Okay, on to learning target number 3. I can differentiate elastic and inelastic collisions and explosions. I can use mathematical thinking to correctly apply the law of conservation of momentum. Now, you may have heard of conservation of energy or conservation of mass, and so we have a similar thought here, just like how mass and energy are conserved within a closed system, so is momentum. And this is seen in a couple different types of interactions: elastic collisions, inelastic collisions, and explosions. Okay? So first let's define what we mean by elastic collision versus inelastic collision. So in an elastic collision, that means two objects, they impact, they interact, and then they essentially just bounce off of each other without deforming or changing the objects from their initial composition. Okay? So a great idea looking at something like this would be if we had two bouncy balls, right? And they just bounce off of each other. Or we have some like carts on tracks that have springs. And so if we push one of the carts and it hits the other one and it bounces it forward, that's an elastic. Now, in an inelastic collision, it's when the two objects, they're deformed after the collision or heat is produced, but the most common thing that occurs is that they stick together, that they usually like kind of crumple together and become one object. That we went from like two separate items and then we had a collision and we ended with one connected item. Okay, so that's the difference between elastic and inelastic. In both situations, elastic, inelastic, and explosions, momentum is conserved. So meaning that the momentum that we started with is the momentum that we have to end with. Okay? If we look at one of those objects individually, we can't perceive that momentum being conserved. Like if we look at the picture of the car here, we have this initial velocity and then the car has some mass, right? And so that it's relatively big, it's going relatively fast, so we have a relatively large initial momentum. Then it crashes into the wall, and then it comes to a stop. And so the final momentum is 0. So you could say, well, momentum wasn't conserved because I started with momentum and I ended without it. But if you look at the system as a whole, which includes the wall and, the earth that the wall is attached to, it turns out that when the car hit the wall recoiled a little bit. Or, like the earth, the wall, altogether, there was a small recoil, which accounted for the other side, the conservation, the final side of that momentum. It was essentially transferred from the car to the wall or the earth. Okay. When we can see this the best is when objects have similar mass. Like the previous example with the wall and the earth is so much more massive, or even like the wall component is so much more massive that it's hard to observe that conservation of momentum. But it becomes more obvious when we have similar objects, similar size or mass objects. So something that you might have seen before. If we have two cars relatively the same mass, and car 1 here approaches with a greater velocity, so it catches up and it bumps into car 2. Well, then what happens? Car 2 is kind of propelled forward. And again, we're talking about these perfectly elastic, like it's not deformed at all. So car 2 gets bumped forward, so its velocity increases. Car 1, it decreases. And momentum is mass multiplied by velocity. And so they can switch, or there's a ratio of those velocities there that we start and end with the same momentum. Mathematically, this is what it looks like. we can look at the change of momentum of these cars individually. So for number one, we have a change, right? We have a final momentum minus an initial momentum, and the change in momentum is equal to the impulse, which is the force applied. But what force are we talking about? Because we need to be clear about this. We're not talking about the engine propelling it forward. We're talking about the forces involved in the collision itself. And so it's this time, this interaction where the cars are in contact with one another. And so it's actually the force of car 2, the force of car 2 pushing back on car 1. Okay, so I would call that the force of car 2 on 1. And then we can look at the change of momentum of the second vehicle, so final minus initial, and that is equal to impulse. And that's the force involved, delta t, the time it was applied. But again, we're talking about the crash, about the interaction, the collision. And that is for car 2, that would be the force of car 1 on car 2. So it's an action-reaction pair. It's a Newton's third law pair that's happening there. And the time component would have to be the same because it's the same collision. Car 1 was interacting with car 2 for just as long as car 2 was interacting with car 1. Okay? So it's a Newton's third law pair. So that must mean that the force of car 1 on 2 is equal and opposite to the force of car 2 on car 1. Okay? If we set those equal to each other, and the time component's the same, right? So this must equal that, okay? Except the opposite component, right? They're equal in magnitude, opposite in direction. And so we have to apply that negative. So we could say that the change in momentum of 2 is equal to the change in momentum of 1, but in the opposite direction. Now, this is something I find really interesting. Let's see, we don't have a lot of room in our notes. I'll write it down here, okay? Delta P2. So what we mean by this is momentum final of 2 minus momentum initial of 2. Okay, that's our delta P2. And this is going to equal negative momentum final of 1 minus momentum initial of 2. Or I can distribute that negative. And so it could be negative momentum final 1 plus momentum initial 1. Okay? And then I can rearrange this a little bit. I can add this to the other side, and I can add that to the other side. So that would be momentum final 1 plus momentum final 2 will equal momentum initial 1 plus momentum initial 2. And so here's our conservation of momentum. It's saying that if we have the sum of the momentums in the final state is going to equal the sum of the momentums in the initial state. Whatever we start with is going to equal what we end with. And that's what these little primes mean. It just means final. It's another way of looking at that. I'm going to stick with these subscripts here. I think they provide a little more clarity, but it's saying the exact same thing. It's saying that whatever momentums we started with, we have to end with, okay? So again, we could call this sum of the momentums final, right? Because we're adding them together, is equal to the sum of the momentums initial, or you could flip-flop those. You could say the sum of the momentum initial is equal to the sum of the momentum final. What we start with is what we end with, so we see conservation of momentum. Okay, this just is talking about the same thing. And we talked about that law of conservation of momentum. And then again, we're just recognizing the difference between elastic, inelastic, and an explosion. In an elastic collision, there's a collision, but nothing is deformed. They bounce off of each other. This is an example with cue balls, with pool balls there, and they're bouncing off of each other. And then here's an inelastic collision with train carts there, where they snap together, right? Where this one comes into that one, there's a collision, but then they stick together. And an explosion is when we start with one object and it explodes, it separates into at least two other objects. And conservation of momentum is seen in all three of those. Okay. See if I can get to stay focused. Now, still, we have similar idea here. We're just going to talk through the same thing one more time to make sure we're on the same page. So, before the collision, we have a momentum of A initial, and the vector quantities going that direction. Momentum of B initial, the vector quantities going in the opposite direction. There's an interaction where the force of A on B, and we have the force of B on A, where we have our Newton third law pairs that's seen in that interaction over a given amount of time. And then that results in a change of momentum. And so now we're going in a different direction, and we may also have a different velocity as well. Okay, we know it changed, and there's ways we can identify how it changed. It could either be the direction or the magnitude, right? Or both. So before the collision, each ball has momentum. During the collision, we see a Newton third law pair interaction. Write the impulse momentum equation for each of the objects that are interacting here. Okay, so we have, for ball A, we have our momentum final of A minus our momentum initial of A, okay, because that's just the change in momentum. And remember, change in momentum is equal to the force. And in this case, if it's A, it's going to be the force of B pushing back on A. The force of B on A multiplied by the time that the interaction was happening. That the change in momentum is equal to the impulse. And now for ball B, we have that change in momentum, so that'll be final minus initial. And that's going to equal the force of A on B over the same amount of time. Okay. The collision occurred in the same amount of times for both parties involved. So this T has to equal that T. Okay. So using Newton's third law, we know that F of B on A has to equal F of A on B, same magnitude, opposite direction. So that means that this whole thing equals that whole thing, except for what's the negative component of that. So this all equals that, only it's the negative component. Okay, so that means we have momentum final of A minus momentum initial of A is going to equal the opposite of this, right? So this will become a negative, that'll become a positive. So it'll be negative momentum final of B plus momentum initial of B.